welcome to a new week of mini lecture. I'm really excited because this week we have more content than ever. I hope you're not too overwhelmed. I think this is all interesting stuff. So I'm making this introductory, this intro thing, so that we can give you an idea of what to expect in the coming content. So first we'll finish up some loose ends from last week with the max flow, min cut, duality. And then we'll dive fully into duality and talk about that in and of itself. Then we'll go into zero-sum games, and then so that's the content as far as lecture goes. And then we'll have some awesome tutors walking us through problems and examples with duality and zero-sum games. And at the very end, we'll have Abhinav walking through a max flow problem from last week. So I know that last week in lecture, we didn't get to do a very involved, problem running the algorithm. So we asked Abhinav to just pretend he's a student and do this walkthrough as if he's just solving the problem. So it's a really good opportunity for you to, take out a piece of paper and do it with him, or just watch him do it. It'll be a good time, I promise. And this week we're also incorporating some Edpuzzle content, which just means that if you use the Edpuzzle link on Piazza, you'll be able to click, you'll be able to see some questions that we pose to you, and the video will automatically pause. So we'll force you to pause the video and think through some concepts. So hopefully that'll help as well. I'm really excited about all these new things that we're experimenting with, and I hope you are too. So I'll see you later. All right. Bye guys. Hey everyone, welcome to a new week of mini lecture. This week we'll be covering two very exciting topics, duality and zero-sum games. Before we dive in, there's a tiny bit from last week that we didn't get to, and it turns out that it'll give us a really good intuition for what we're covering today. So it all works out. So let's get started. So this tidbit from last time is the idea of a min cut in flow diagrams. Recall that the flow problem is one where we have this directed graph with edge weights or capacities on edges, and we want to transport as many units of flow from a predetermined source node to some destination. Last week we derived an algorithm with the idea of taking back moves, but I never proved why it works. The proof actually relies on the idea of min cut, so let's do that right now. We've seen the idea of a cut before in talking about minimum spanning trees, or MSTs. If you remember, when we covered prims and Kruskal's algorithms, we saw that whenever we take a cut, which is just you take a partition on the number of vertices, so you have like big V1 and big V2, where you have your source maybe in V1 and destination in V2. This whole source and destination thing didn't exist in MSTs, but we're introducing them here. You'll see exactly why. But in MSTs, we saw that the cross edges are just edges that connect vertices that's been separated in this partition, and this definition still holds true here. And in MST, we saw that out of all the cross edges, whichever one has the minimum edge weight or minimum, minimum length, will end up being in the minimum spanning tree. However, here let's sort of repurpose that for our use. We say that in the max flow diagram, we partition the vertices the same way. We take two partitions and put them into V1 and V2, where the source node is in V1 and the destination node is in V2. And now we take all the cross edges that are just edges whose vertices, end vertices got separated by this partition, and we say that the max flow cannot be more than the sum of all of these edge weights in the middle. So think about that for a moment. It just says that because we need to get from node S to node T, we eventually have to pass from the set V1 to the set V2. And in passing that, you inevitably have to pass through these edges, and if these edges don't have enough weights or capacity, we're not going to be able to get that many units of flow across. So this is sort of our bottleneck. So what we derived here is that the sum of over all the edges in the cut, all the cross edges in the cut, you take the sum of all of their capacities. Capacities is denoted by C, of these edges. This has to be greater or equal to our max flow. So it says that you can't transport more units of flow than you have, I guess, capacities available in this bottleneck. So now that we have this upper bound, we want our upper bound to be as small as possible. This is a common theme, right? You have an upper bound, and you want this to be as tight as you possibly could make it, so that you want it to almost coincide with what your actual max is. So in this graph on the right side, which we saw last week as a simple example of our algorithm of finding max flow, I'll ask you to pause this video, and we're doing something new here. Maybe this week we'll have Edpuzzle, so maybe you'll have to pause this by default. But pause this video and think about what kind of cut you could take so that this sum of all edge weights in the middle is as small as possible. Okay, I assume that you've paused the video and thought about it. So it turns out that the best one you could take is right here, where your V1, your set V1 is just this source node, and your V2 is T as well as A and B. So this tells us that the edges that are affected, the edges that got cut, was 1 and 1, so the sum of edges is 2, and we say that this is bigger or equal to the max flow. We saw that last week in this problem using our algorithm, we could get a flow of 2, right? We just send 1 unit flow up top, SAT, and 1 from the bottom, SBT, and we in fact got our desired flow. And this just tells us, this whole min cut thing just tells us that that is in fact the optimal. We can't have anything, we can't do any better than 2. So in a sense, even though min cut and max flow seem like really different problems, one you're maximizing and the other you're minimizing, they seem to have this very intricate correlation with one another. They seem to relate to one another in a sense that the min cut problem gives an upper bound on the max flow problem, and in fact, this upper bound is actually achieved. So the max flow and the min cut actually coincide, and they provide a sort of certificate of optimality for each other. So, I don't know, they're sort of accomplices, or whatever you call it. They prove each other innocent. They prove each other optimal. So we can think about this, zooming way out and say, these two problems have this special property. What about other problems? If I have, just a general linear programming problem, can I find their evil twin that justifies them to be optimal, or something like that? And so it turns out the answer is yes, and we're going to cover that in the next segment when we talk about duality. But for now, even as we put min cut and max flow on the back of our mind, sort of behind us, we still want to remember the defining qualities that interested us, the two qualities of the quality that the two problems bound each other and give a certificate of optimality if their values coincide. Okay, I'll see you in the next segment. All right, let's get started on duality. So last week, you might remember this question about studying for 170. I hope you took this to heart, but more importantly, I hope that you remember how to derive the linear program for this problem. If this looks very unfamiliar to you, or you've forgotten how we got here with all the objective and constraints, I encourage you to go back to last week's mini lecture and just brush up on that, because we're going to take this for granted and just run with it from here on out. So last week we wrote down this linear program, but this is before we cover the algorithm and before we justify that any optimal will occur at a vertex. So we never got to actually solve this linear program. So I encourage you to pause the video now and using the graphic approach of finding vertices, find the optimal happiness value that we're maximizing using what we covered last week. All right, so I hope that you've paused the video. This is so very weird, just looking at a screen and hoping that whoever's watching this actually pause the video and solve this by yourself. But The idea is, well, now that we have this feasible region and these green lines that indicate the objective function, we can push it as far as possible in this direction, until it reaches the last point that it can intersect with the feasible region, which turns out to be this white point right here. So here, solving with x2 equals 7 and x1 plus x2 equals 12, we get the solution that the optimality happens at the point 5, 7, where you have, this is your x1 and this is your x2. So now you can say that the optimal value, your value of happiness, is max happiness is just 5 plus 7 times 2, which is, x1 plus 2x2, and you'll get 19. So this is a great way to solve this. I hope this is, you got that. And but maybe last week when we were covering this problem, you might be thinking, this is a bit of a silly problem. I can use some of my clever equation manipulation to actually solve this in a better way. And you might be correct. So this is how I thought of this problem before I learned linear programming. I would say, well, I want to maximize x1 plus 2x2, so maybe I should construct this x1 plus 2x2 with these constraints I'm given. So maybe the first thing I thought of was taking the first two and combining them to, take one copy of the top and then 2 times the bottom. So on the left side, I'll get x1 and then 2x2. So this is, this times 1, this times 2. I hope you can see that. This is blending in. But on the right side, you'll get 7 plus 14, which is 21. This is a smaller equal sign because these are smaller equal signs. And that would be, that would be perfectly reasonable. It turns out that, our happiness is indeed smaller than 21, but this isn't super optimal. So maybe I'll try again. Maybe I'll take the second and the third, and I'll take one copy of each, and I'll get x1 plus 2x2 again, because there's an x2 here, and there's x1 plus x2, and I'll say that I get 19. And since I could get 19 here, since I could get maximum happiness as 19, then, this is optimal, and we're done. So you might be thinking this is just some clever tricks trying to construct equations from constraints, constructing our objective function from the constraints and finding bounds that way. It turns out that this is, the foundation, this is the grounds for discussing duality, that by manipulating these functions in a, systematic way, we can get an optimal value, and we'll see how we do that. So let's do this in more generality. I was sort of guessing when I say I take one copy of this, 2 copies of this, I'll pick equation 2, equation 3. But you could imagine that if you have like a million equations, this would be extremely hard to do. So let's write it this way. Let's write our objective function right here. We're maximizing x1 plus 2x2, and we'll put our constraints here. And these are the candidates that we're scaling, right? We're taking some multiple of these things and summing them up. So I take the constraint x1 smaller than 7. I'm just copying down all of these constraints so that we can use weights on them. Great. Okay, so now I can put on the left side weights. All right, so I'm just going to assign some variables. I'll assign weight y1, y2, y3. I won't assign anything to x1, x2 bigger than 0. We'll just have to, keep track of this because everything else is smaller or equal to, and these are a little bit jarring. So we'll ignore them for now, but you'll see that it doesn't hurt us too much. All right. So if we scale these, we'll be able to write this following equation as we did before, where you take y1 times x1 on the left side, plus y2 times x2, plus y3 times the sum of x1 and x2. And on the right side, you still keep the smaller or equal sign. And on the right side, you get 7y1, 7y2, and 12y3. Okay? And so this is our form for, this is what we get when we weigh these things. But let's reorganize this left side a little bit so that we have some coefficients for x1 since we're interested ultimately in x1 and x2. So we'll take y1 plus y3 of x1. My throat is giving out. And then I'll take y2 plus y3 of x2. And on the right side, we keep everything the same as always. So now you might be thinking, well, now this should match what we have up here, right? Ultimately, we want to say that this left side is the objective function and the right side is whatever bound that we can find for that objective function. And you would be completely correct. So I want this, this coefficient for x1 to be 1 and this coefficient for x2 to be 2. But really, I can do, I could make it 1 and 2, but I could make it bigger since x1 and x2 are positive numbers anyway, so we're using this criteria that x1 and x2 are bigger. So if we have that there are bigger coefficients and it's still smaller than these things, that would be even better, right? We have no trouble with that at all. Okay, so we can say that y1 plus y3 should be bigger or equal to 1, and y2 plus y3 is bigger or equal to 2. And let me just say one more word on this. We can make it bigger because if these things are bigger and this is satisfied, then the smaller version, taking 1 and 2, would in fact satisfy this as well, since x1 and x2 are bigger than 1. So, taking higher coefficients will only make our left side bigger, and if it's still smaller than the right side, then it doesn't hurt us. I encourage you to pause the video if you want to think about this through it. It did take me a while to understand this when I was first learning it. So I get these two constraints on the y's, and ultimately I want to say, what is my objective? What I want to do? I want to minimize this right side. Remember how we said in the previous demonstration on Maxwell and Mincut that when we have an upper bound for something, we want this upper bound to be as strict as possible, which means you don't want your upper bound to be infinity because basically you don't have an upper bound. Instead, you want your upper bound to be as small as possible. So in this case, we're trying to minimize this upper bound of 7y1 plus 7y2 plus 12y3. Oh, my mouse is glitching. But that's okay. So you might be thinking, you end up getting a linear program. This is looking more and more like a linear program. You have an objective function, you have these constraints, and we have one more which just says y1, y2, and y3 all have to be bigger or equal to 0. And this is just because we are multiplying weights, and we're multiplying these weights with these constraints, and these constraints are inequalities. So you don't want to multiply inequalities with some negative number because, we've assumed that we can write this smaller equal to sign without having nightmares. So to ensure that we don't have nightmares going forward, we also have all the y's have to be bigger or equal to 0. So now I'm going to box this up, and this will end up being our dual linear program. This is the dual LP. What this means is that any solution to this linear program right here will end up giving us an upper bound on the solution for our previous linear program. We call that one the primal linear program. I'll write this here. This is the primal LP. Right. So all of the things that we have in the dual are things of this form. And once we find the minimum one, we can say that regardless of what that is an upper bound for this linear program. All right. So it turns out that there is a general theorem that we'll cover later on that says the dual linear program and the primal linear program will have the same optimal value. So the objective function at the value of the objective function here will end up coinciding, but we haven't gotten there yet, so this is sort of, a sneak peek. But for now, let's see how to write a linear program in general, because, this is a little bit, the way we did it was a little bit hand-wavy. You just, the idea is there, you put some weights on your program, but then, what else do you do? If I hand you any old linear program, how do you give me the dual? So let's talk about that right now. I've written the primal and dual linear program here on this on the blackboard or whatever you call this, and we can say that to generalize this objective is just the max of some CTX. So C and t are, what's it called? They are vectors. So these c's are just 1 and 2. So here c is like 1, 2, and then x is x1, x2. And then so once you take, I don't know, the, once you take, oh, okay, well, once you take, these are vectors 1 and 2, and then x is x1, x2, and once you take the transpose of this, you'll get, 1, 2, and then you multiply this, and by matrix multiplication, you'll get x1 plus 2x2. And this is just a fancy way. We'll just say that, this is your vector c, and this is your vector x, and they all can have, many terms. All right? And then here you say ax is smaller equal to b. And what this does, well, this just tells you all of the equations. B is just 7, 7, and x is x1, x2. And then you can decide what your a is, and that just gives you some linear combinations of your x1 and x2 on the left side and some stuff on the right side. This is just a fancy way of writing all of these constraints in a huge, in a fancy matrix manner. And in this particular case, when we want to get x1 smaller equal to 7 and x2 smaller equal to 7, we'll just put 1 here and 1 here and put zeros. And if you want, you can pause the video and think about why this is exactly what we have on this side. All right. Oh, we have one more. Great. We also have that x1 plus x2 is smaller equal to 12. That's fine too. We can just add one more, and then we can extend this guy to hold 1 and 1. And again, feel free to check. This will just give you x1 plus x2 is smaller equal to 12. Let me write this a little bit better. All right. So that encapsulates all of these criteria. And this last one is just x is bigger or equal to 0. That just means every term in x should be bigger or equal to 0. All right. Now we're going to look at the dual. Let's notice what the objective function is. The objective function, we're minimizing now. Notice that this is different. Let me put this in color, that if we're maximizing in our primal LP, we're minimizing on the other one, because you want them to, go in different directions. You want one to go down from the above, and you want one to go up from below. So we have minimize, and we say YTB. So what's B? B is this guy. So this is our B. B is right here. And we see that, B is the 7, 7, 12, and then YT is just Y1, Y2, Y3. And we can see that this matches perfectly, right? 7Y1, 7Y2, 12Y3. Right? So this is our objective function. And now we go into the actual constraints, and we see the constraints is Y transpose A is bigger or equal to C transpose. Okay, this is a mouthful, but we're going to see that this is exactly what we're just saying here. It's nothing new. What's YT? Y transpose is just, it's a row vector, as we had on top. So it's your Y1, Y2, Y3. And then your A is the same A that you had here. This is 1, 0, 1, 0, 1, 1. And we say this is equal to CT. CT is this guy right here. 1, 2. And you can see this works out. Y1 plus, actually, you know what? You can pause the video here and try to expand all of this out, and you'll see that even though we wrote this in such a fancy manner, this is nothing more than saying you get these weights after multiplication right here. All right? And in the end, you have y is bigger than 0 right here, which just says every term in y is bigger or equal to 0. This is why we can even multiply, because multiplicative weights should not change the direction of our inequalities. Okay, so in the end, we have these things that given some primal LP that looks something like this, we can write out the dual like this. Okay? So this is how you construct the primal LP, or you construct a dual LP from the primal. This is the formula per se. All right, so that was a little bit hand wavy, but the idea is, you do these multiplicative weights and you have constraints on the weights, and you want whatever is the objective function on the right side to match what we want on the left side. Here's the kicker. Okay, maybe, I don't know, maybe I shouldn't label this as the kicker. This is, let's make it fancier, let's call it theorem. The theorem is that duality gap is 0. What is duality gap? So this is your primal function, so this is your primal LP, and this is its feasible region. And this is all of the values that it could take because we're maximizing, right? So this is the max. This is the max, and below it are all the values that we could take. And for the dual, this is the min, and going up are all the things that we can take. The theorem says that this gap right here is 0, that there is no gap. That whatever is the optimal for your primal is also the optimal for your dual. So basically what this says is max objective of your primal is equal to the min objective of the dual. And this theorem gives us the result that, for example, we have min cut equals max flow. All right, so I'm not going to prove this here. If you're interested in the proof, you should look online. It's very interesting, I'm sure. But the idea is, whenever you construct a dual program from a primal, you're guaranteed that their optimal values coincide. And that's, super surprising in a way, right? You have these almost like super different linear programs, and you get the result that they in fact have the same optimal value. All right, that's it for today's lecture on dual linear programs, and I'll pass it off to Neil, and he'll be covering zero-sum games. All right, thank you guys.
Hey everyone, in this video we'll be covering zero-sum games, which is covered in 7.5 of the textbook. So the premise of zero-sum games is they're basically, games where whatever one player wins, the other player is going to lose that exact same amount, right? So if we have a game, for example, and there's two players, player A and B, if player A wins 10 points, that means player B is going to lose 10 points. Player A wins 5 points, player B is going to lose 5 points. If player A wins 0 points, that means player B is going to win 0 points, right? So it's basically games where the net amount that is won and lost is just becomes 0, right? And so before we go into what, how this connects into linear programming in 170, just want to give a brief, quick example. So essentially we have, for example, in the simplest game out there, rock, paper, scissors, we have this thing called a payoff matrix, which details the profits and losses gained by each player, depending on the outcome of a game. And so here we have player 1, which we just call row, and player 2, which we call column, right? And so if we take an example, right, if the row player plays a rock and the column player also plays a rock, the winnings is 0, right? It's just a tie. But if the row player plays paper and column plays rock, then the row is going to win. And we just, kind of arbitrarily gave a winning score of 1 and a losing score of -1. And so if you'll see here, let's erase this. If you'll see in this payoff matrix, it becomes apparent that this is kind of in the row's perspective, right? So if row wins, that means it's going to win 1 point. But if column wins, that means row is going to win -1 points, right? And that's apparent here, right? So if row plays like scissors and column plays rock, which means column's going to win, we have a value of -1. And so -1 basically is benefiting column. That means column wins a point. And so that's kind of like the gist of like, the logistics of the game, right? And so the expected payoff or the expected winnings is we just take an expected value for each for each element in the matrix, right? So for this element, it's basically what's the probability that column plays a rock times what's the probability that row also plays a rock times the winnings that we get from that outcome, right? And we basically do that for every single element in the payoff matrix, right? And the reason why probabilities are involved here is that you know the whole point of this game is that each player is trying to win the most, um, the maximal amount, right? And so if row kind of always plays rock, let's just say like row has a really basic like strategy. Row's just always going to play rock, right? Then what column is going to do is column is going to see that and learn from that. Be like, okay, how do I beat rock every time? I'm just going to play paper every time, right? So if row just plays a really simple strategy, just like playing rock every time, that means column. It's going to be really easy for column to beat row every single time. And so that's why it kind of, it would make sense for row to switch things up, right? That's why anytime you play rock paper scissors, you're not just going to play the same element every single time. You're going to switch it up, right? And so that's where probabilities come in, right? So to find the expected winnings from this game, we just take the expected value over all 9 possibilities here. And so we get this expression right here. And so here, xi is like the probability that row plays element I, and yi is the probability that column plays an element I, right? And g sub ij is the winnings from that outcome, right? So again, just to be really clear, since the payoff matrix is in the row's perspective, this value, this expected value, this expected payoff is also in terms of the row's perspective, right? The row is trying to maximize this expected value, whereas the column wants to minimize it. Yeah, moving on. So quick question, for you guys is what would be the best that the row can expect to do, right? So like, the row, like regardless of what strategy the column plays, like what is the best that the row can expect to do? And so kind of to answer that question, let's take a look at the payoff matrix again. And let's just bring up a sample row strategy, right? Let's just say row plays rock 1/3 of the time, paper 1/3 of the time, and scissors 1/3 of the time. So basically row plays like purely randomly, right? And then let's just analyze some strategies that the column could play, and let's look at the results, right? So let's just say column has, a really basic strategy. It's going to play rock 100% of the time, right? So I'll just say 1, 0, 0 to denote the probabilities. And so if we want to find the expected winnings, the expected payoff from this, we'll see that, we literally just plug and chug into this equation, into this expression. And what we'll see is, the probability that row plays rock and column plays rock is just going to be 1/3 times 1. And then the payoff from that is just 0. And then we just keep iterating through all the possibilities in the table. So going on to the probability that row plays paper is 1/3. Probability that column plays rock is 1. And the payoff that we see is 1, right? That's this one. And then the next one is, let's analyze this one. So that's going to be 1/3 times 1 times -1, which is a payoff from it. And then that's actually all the elements we care about, because all the other ones are going to have a 0 term, right? Because the probability that the column plays it is 0. So we're just going to put 0 for the rest. And so what this ends up evaluating to is 0 plus 1/3 minus 1/3 equals 0. And 0 is the expected payoff that the row expects, right? It can't expect anything more, given this strategy that column and row play. And so let's look at another strategy maybe. Let's look at, let's say column switches it up a little bit now. Let's say column plays rock 1/2 of the time and column plays paper 1/2 of the time, and scissors, just ignores scissors, right? Now the expected payoff is going to be, let's see, kind of going down each row. We'll see that, let's see, for rock and rock to happen, it's going to be 1/3, 1/2 times 1/3 times 0 plus 1/2 times 1/3 times 1 times -1. And then before I do the next column, before I do column, before I analyze this column, let's just observe a small thing here, right? So we can immediately factor out the 1/2, which is basically the probability that the column plays rock. And the thing is, we can also factor out a 1/3 from here, right? Because row plays rock, paper, and scissors, each 1/3 probability, so we can just factor that out. So what we're going to be left with is 0 plus 1 minus 1. This, as you'll see, simplifies out to 0, right? And so this entire expression becomes 0. And what we'll see is if we do the same analysis, the expected payoff for this column, when column plays paper, we'll see that it also evaluates to 0. And then obviously here, it's also going to evaluate to 0. So the entire expected payoffs become 0. And so what you'll see here is that whenever row plays a completely uniform distribution, right? It plays its options or its elements completely at random, 1/3, 1/3, 1/3. We'll see that the expected payoff becomes 0, right? And that's because we were able to factor out this 1/3 out of everything. And we see that the sum at each column becomes 0. So that means whenever a row, and this works, by the way, if column does this as well, right? If column plays its options completely randomly, we'll see that the expected payoff here becomes 0 as well. Yeah, which is kind of surprising. It basically means that regardless, so the answer to this question, going back to this question, is what's the best the row can do, or what's the best the column can do? They're kind of equivalent questions. The best they can do is expect 0 winnings, right? Because no matter what row does, or no matter what column does, the other player can just play at complete, random. The other player can play completely random, and the expected payoffs is just going to be 0. So the whole strategy behind rock, paper, scissors is just to play at completely randomly. And that's the best you can expect to do. So moving on, let's consider the possibility. Let's consider what happens when you're forced to announce what your strategy is, right? So let's say in the rock, paper, scissors example, let's say if you were row and you decided for some reason your optimal strategy was, like, you were going to play rock 1/5 of the times, scissors 2/5 of the times, and like paper 2/5 of the times, right? Let's kind of like look at what would happen if you were forced to publicly announce what your strategy was. So it turns out, again, so just to make it super clear, we're operating under the assumption that both players in any game that we look at are going to play optimally, right? So row is what this means is row is going to want to optimally maximize the expected payoff, while column is going to want to minimize the expected payoff as much as possible. So that's kind of like the assumption we'll be moving forward with. And so if we're kind of forced to announce your strategy, like let's say, let's take another example, right? Let's say you're playing a game and you're forced to announce your strategy, right? It would seem that like it would seem like the other player would then have the advantage, right? Because they know what your strategy is in advance. But what we're going to realize here after doing some, math is even if you announce your strategy in advance, as long as, we're operating under the assumption that both players play optimally, that's not actually going to hurt your expected payoff, which is kind of like insane. And like, it basically means that even if you tell the opponent your strategy, it's not going to help them out, right? As long as both players are playing optimally. But let's look at an example to make that, somewhat actually believable. So let's look at a new game, right? Here, again, there's row and column. And let's say row has, player options of like A and B, right? It can do action A or action B. And column can do action C or action D. And the expected payoffs, the payoffs for each action are here, 3, -1, -2, right? And so let's look at a couple like basic examples, right? Let's say row plays A with probability 1 and B with probability 0. So let's kind of see what would happen depending on what column plays accordingly, right? So if this basically means that row is going to play A every single time. And that basically means, if column then plays C, what's going to happen is you're going to take, if column plays C, what's going to happen is, we'll look at this column exclusively. And the probabilities are then 1, 0, right? So the expected winnings, the expected payoff is going to be, 1 times 3 plus 0 times -2. So the expected winning here is just going to be 3. What if, the expected winning is going to be 3. What if column plays D according to row strategy, right? Then the expected winning is going to be 1 times -1 and 0 times 1. So this is just going to be -1. Again, where did I get these values from? Here, in this strategy, row is playing A with probability 1, which means row is playing A every single time. And so if column plays C, it's going to be 3 times 1 is the expected payoff. And if column plays D, it's going to be -1 times 1. What if row plays with the strategy 1/2, 1/2, which basically means that row randomly picks between option A and B. The expected payoff then is going to be if column plays, option C, the expected payoff is going to be 3 times 1/2 plus -2 times 1/2, which is just going to be 1/2. And in the D case, it's going to be 1/2 times -1 plus 1/2 times 1, which is just going to be 0. So again, just to make this super clear, in this case, if row plays with the strategy 1, 0, and let's say row announces it publicly, right, that it's going to play A with 100% probability, it becomes clear then here the expected payoff is higher if column plays 3. And again, column's main goal is to minimize this, right? So it seems like under row strategy where it plays A with 100% probability, column is going to wants to play D. The column should play option D every single time in order to minimize the expected payoff. And it seems like here the expected payoff from C is greater than the expected payoff from D. So kind of same thing here. Column's going to want to play option D. And so the main point to take away here is that whenever row announces her strategy, column is going to have a clear-cut strategy to play, right? So if row announces her probability or her strategy, what column can do is column can compare, all right, what's my expected value if I play option C versus what's my expected value if I play option D, compare which one's higher or lower. In this case, column is going to want to minimize that value, so column's just going to choose the minimum of that, right? And so kind of generalizing this, here I use some exact values, specific values for the probabilities, but generalizing this further, let's say row plays option A with probability x1, and row plays option B with probability x2. Then let's compare the earnings. Let's compare the game's payoffs depending on if column plays option C or column plays option D, right? Here, if column plays option C, the expected earnings is going to be, let's see, looking at it, it's going to be 3, -2. So it's going to be 3 times x1 minus 2 times x2. Again, this kind of like, this comes from the exact same math I used in these examples, right? Again, we're doing expected earnings. If column plays D, what's the expected earnings or expected payoff? It's going to be -1 times x1, which again is just this value, plus 1 times x2, plus x2. I can get rid of this, actually. It's just going to be -x2 plus x2, sorry, -x1 plus x2, right? Again, when, just to be extra clear, this table kind of like, sorry, the left side of this table is representing if column plays option C. And the right side of this table is if column plays option D. And the reason why I'm viewing this in a sort of binary context, it's not like column's going to play option C with 1/2 probability and D with 1/2 probability, is that depending on these two values, column is going to choose whichever one's smaller, right? Because column wants to minimize the expected payoff, right? So it's going to minimize, it's going to choose whichever one of these is smaller, right? So I made that point here. Column is going to choose the minimum of these. But yeah, so the expected payoff of the game is going to be either this ugly arrow or this. And so now what we have to think about is, what is rho going to do now, right? Rho is then going to design x1 and x2, which is, again, the probability of choosing A and B, to give her the best payoff, right? Okay, so I just want to drive home, this point. So this is kind of like a diagram explaining the logic of how this works, right? So step one is basically rho announces, her strategy, right, to the public, in public, right? What column is going to do is column is going to see which option, C or D, helps minimize the expected payoff as best as possible, right? So column is going to want to minimize the payoff by choosing either C or D to play every single time. But the thing is, so that's kind of how it looks, to the public eye, right? But what's going to happen is this dotted arrow, right? The second flow of logic. Again, we're operating under the assumption that both players play optimally, right? So the rho player knows that column is going to play optimally. So what rho then does is, knowing that column is going to want to minimize this payoff, rho is then going to design an optimal strategy, x1 and x2, such that the expected payoff is still maximized. So it might be a little bit confusing the first time you hear it, but there's basically two levels of logic, right? Rho knows that column is going to minimize it, so rho designs an x1 and x2 so that it's maximized for her, right? And so if that's a little unclear, hopefully this next expression is going to make that a little more clear. But basically, again, column has two options, right? Playing C or playing D. And this is the expected payoff of C, this is the expected payoff of D. So, and column is going to choose the minimum one of those, right? So this value is literally what column wants to minimize, right? And that's going to be the resulting entire value of the game, right? But the thing is, when rho is deciding her strategy initially, rho is going to choose an x1 and x2 such that this whole expression is maximized, right? What that basically implies is, no matter how optimally column plays, right? Even if column plays as optimally as possible, rho still has a way of choosing x1 or x2 to mitigate how low the expected payoff goes. And so before making it, even if it's a little confusing, let's just, stick with this even on the other side, right? So again, in this problem, in this game, for example, there's two players, row and column. So far, we've been looking at it. All right, how does row choose her optimal strategy? We can do the same thing for column, right? How does column choose his optimal strategy? So again, I copied the expected, the payoff matrix here as well. And so if you call y1 and y2 the probability that, y1 and y2 are column strategy. So y1 is a probability that column plays C, y2 is a probability that column plays D. We can do the same thing here, right? Again, row is trying to maximize the expected payoff, right? So in this case, if row plays A, the expected payoff is going to be 3 times y1 minus -1 times y2. And if row plays B, the expected payoff is going to be -2 times y1 plus 1 times y2, right? And among these two options, row is going to choose whichever benefits her the most, which is going to be the greater of the two. So row is going to choose the maximum one of these two expressions, right? And row is going to then play that play that respective option, right? So if 3y1 minus y2 ends up being larger of the two values, then row is just going to play option A every single time to maximize the expected payoff, right? So that's what row is going to try to do. But then in the column's perspective, column is going to want to design a y1 and y2 probabilities such that this whole expression is minimized. So in the first case where we were designing row strategy, row is going to try to maximize a minimization expression. Here, column is going to minimize a maximization expression, right? It kind of works two ways, right? And so let's kind of, so even if that's a little unclear, let's kind of like push forward. So now, let's tie it into 170 concepts, right? Linear programming and linear programming, right? So the moment you see, maximize x1, x2, maximize some sort of expression, you're gonna, that you can express this as a linear programming problem, right? So in this case, let's just, for simplicity's sake, let's just call this whole thing z, right? I wrote that here. So let's say z equals the minimum of 3x1 minus 2x2, comma, negative x1 plus x2, right? And so we want to maximize z. We're gonna want to maximize z, right? That's our whole goal, right? Again, this is in row's perspective, right? We want to maximize z. The next thing is we know that since z is a minimum of these two, since z is a minimum of this and this, we're going to know that z is less than or equal to 3x1 minus 2x2, and z is also less than or equal to negative x1 plus x2, right? Again, it's literally just because we defined z to be the minimum of those two. And there's two remaining factors for the linear programming problem, or the linear programming representation. It's that we know that the probabilities have to sum to 1. The probabilities are x1 and x2. So we know that x1 plus x2 equals 1. And we also know that probabilities can't be negative, right? So we know that x1 and x2 are greater than or equal to 0. And so these expressions, or inequalities and equalities, are our LP representation. So, in row's perspective, we can do the exact same thing in column's perspective, right? We can come up with a linear programming representation for a column's perspective as well. And so here, again, this was the thing that column was trying to minimize. Column was trying to minimize here. And I think in the textbook they called this maximize the max of 3y1 minus y2 comma negative 2y1 plus y2. I think that they call that expression w. So I'm just going to use that same variable. So here it's a minimization problem. Again, it makes sense because, again, column always wants to minimize. So we're going to want to minimize w. And since we're setting this whole thing to w, we know that since w is the maximum of these two things, we know for sure that w is greater than or equal to the first the first expression. And we also know that W is greater than or equal to the second expression. So we can just write those down, write those two factors down, or write those two inequalities down. We also know the probabilities have to sum to 1. We also know that probabilities have to be greater than or equal to 0. So again, this is another LP representation, except now it's in, just to make it clear, columns perspective, right? So all we did was, in both cases, in Ro's perspective, Ro is designing her probabilities, keeping in mind that column is going to play optimally as well. So she knows that column is going to minimize some value. So Ro is going to want to choose probabilities that maximizes it. Basically, Ro wants to maximize the smallest possible payoff that she can get. And column is going to want to minimize the largest possible payoff that's possible. So my question to you is, how are these two linear programmings related, right? So we have two linear programming representations for the same problem, except one is in Ro's perspective, one is in column's perspective. So how are these two related? And the answer is they're duals of each other. And I highly recommend you, kind of like using Lily's, mini lecture, go through the math and verify on your own that these two are duals of each other, right? But anyway, moving on to the ramifications of this, knowing that they're duals of each other then tells us that the optimum value achievable for both, for row as well as column are going to be the same, right? And we know that from, again, the duality, mini lecture, right? Duals of the same linear programming problem are going to have, the same optimum value. So yeah, if row and column play optimally, that value is going to end up coinciding, right? And so we saw that, way earlier on when we looked at this rock, paper, scissors example, where we saw that, the expected payoff in both cases, if both people played optimally, the expected payoff is just going to be 0, which is like for both player, right? Regardless of whether you announce your strategy in advance or you don't, right? So yeah, so going through the math of this, we kind of like looked at how to design an optimal, strategy. We realized that the two strategies, like rows as well as columns, they're going to create dual linear programming problems, which means the optimum value achievable for both row and column are going to be the same. Yeah, thanks for listening.
Welcome back to this week's 170 problem walkthrough. This is my second time recording this because I somehow lost the file, or Zoom did. I hope this time it goes through. Last week we talked about a diet LP problem, and this week our topic is duality. So instead of introducing a brand new problem, I will actually be extending from what we did last week. Last week, our LP problem took the perspective of a buyer trying to obtain all the required nutrients while minimizing the cost. So this week, we are going to the flip side and exploring what it would be like from the perspective of the seller. The buyer now informs us, the vendor, that they intend on purchasing at least this amount of ingredients to meet minimum nutrition requirements. I know this is a bit odd because if I were to present any grocer with this list, I'd probably get kicked out of the store, if not banned forever. However, we'll just say that it is acceptable for the context of this problem. And the vendor thus has this problem to solve. How can I set the cost per kilogram of each of the nutrients? Also sort of weird, I'm sorry about that, such that the buyer will buy from me and I get the maximum revenue. Let's throw back a little bit to the buyer's linear programming problem formation. Our objective function was minimizing this cost function over here while meeting the constraints here from each of the food. And we solve for the amount of food that we are able to buy. The buyer is basically the flip side. The dual of an LP is still an LP. So our approach to the problem does not change. So Just a little throwback. What we did last time is we found the decision variables, the objective function, and our constraints. Very similar for this dual problem for the seller. We're also going to come up with decision variables. We are given that the buyer wants to buy at least this amount of nutrients. So that's something that we can factor into our objective function because we want to be maximizing the total amount that we're selling, which involves the amount that the user wants. So why don't I just try to decide on how much I want to set each unit of each of the nutrients. Great. I think that's a good objective function to start with. However, similar to our last week's LP, we have to figure out what constraints we want to give. Because if we were to only maximize this, we can have unbounded y1, y2, y3s. I can set the price to be $10,000 per kilogram of starch, of plain old starch. Obviously, the seller should be constrained to not do that. So that's where our constraints come in. So this goes back to what the seller actually set in the beginning of the cost per kilogram of each of the food. The buyer obviously will not pay more than 60 cents for food 1, and the buyer will not pay more than 35 cents for food 2. What is everything that goes into the cost of each food? It is actually just the cost of these nutrients, right? So the summation of the total costs of starch, protein, and vitamins should not exceed 60 cents. Hopefully that is quite intuitive, so we can actually use that in our constraints. Given that I am setting my prices of each of the nutrients at y1, y2, y3, the cost of each food is the summation of the price per kilogram of the nutrient times the amount of the nutrients, and we sum over each of the nutrients for each of the food. So this is where I arrive at my constraints here. Just to parse through one of them, just so that we're more comfortable, for food 2, I have 7 kilograms of starch, 2 kilograms of protein, and 1 kilogram of vitamin. And we want to set the prices of each of the nutrients such that the maximum is at most 35 cents so that the customer would still be willing to purchase food 2. And lastly, as I was saying last time, there is this sort of makes sense real life problem restriction where last time we cannot have negative amounts of food that we buy. Similarly, this week, we shouldn't have negative food prices. To conclude this problem, I want to talk about the primal and the dual just a little bit. And this is where duality comes in. For every problem that we try to maximize or minimize, there is an opposite problem that does the exact opposite. However, the optimal solution for the primal is always upper bounded by the optimal value of the dual problem. I didn't mention this, but this is more mechanical. So the number of constraints that we use in one primal problem is the same as the number of variables that we use in the dual. That is just a pattern. You can easily verify it with the LPs that we did this week and last week. A natural question to ask is if the optimal value of the primal solution and its corresponding dual solution would be the same. Naturally, think about this as a chess game. So this is a situation where both you and an opponent get maximal benefit. And the answer is not for every problem, but sometimes. I would suggest looking more into that, as well as the topic of complementary slackness. I believe your textbook covers it. If not, there are probably a lot of papers on these topics. In general, I would say the duality is beautiful because it is two sides of the same coin. It is super applicable in game theory, optimization problems, and maybe sometimes your primal isn't as easy to solve, so you try to solve it with the dual. And by solution, I do not mean the solution to your decision variables. What I mean is your objective value that you get from the function using the decision variables. So this setup might be reminiscent of min-max trees or game trees if you took 6UMB with Professor Hillfinger. So I believe in the game tree, at every other level, you have a maximizing level, which represents player A, for example. And then in every other level, you have player B. Each player is trying to maximize their own winnings. When one player maximizes their own benefit, they are causing loss in their opponent's winnings, which is why minimizing your opponent's winnings is the same as maximizing your own winnings, if that provides more intuition. So this alludes to the zero-sum game problem, which a fellow tutor will cover in this video as well. I think it's really cool once you see the application of duality. And I just wanted to say that if you want more intuition, like think about real life situations where both parties are like in competition with each other to reap the maximum benefit for themselves. Life is not a zero-sum game, but yeah, there still are some cases where it applies. Duality's cool, check it out. Like every other problem that we talked about, I try to like gain intuition around it. That's about all I wanted to talk about today. And feel free to post on Piazza if you have any questions. And I hope you have a fantastic week. And see you next time.
Hey everyone, in this segment I'm going to be going over zero-sum games. So in a zero-sum game we have a payoff matrix like this. We have a row player and a column player. Here in this game we have two actions, A and B for the row player, and the column player can take one of two actions, C or D. And then in here in the grid you can see the corresponding payoffs. So positive numbers are good for the row player and negative numbers are good for the column player. You can think of this as a score where the row player is trying to maximize the value in the grid while the column player is trying to minimize this value. So if row were to just pick an action, like let's say if row picks A, then the column player would pick C and then get a payoff of -4. That's good for the column player. So instead of picking a pure strategy where row just picks one of the two actions, what we're going to do is use a mixed strategy. So a mixed strategy is a randomized strategy, which means that row's strategy can be represented as a vector x, where x is x1, x2, so it's a vector of two elements. And these two numbers are probabilities. So x1 is the probability that row picks A, and x2 is the probability that row picks B. And we can do the same thing with the column player, where it's represented by two numbers, y1 and y2. So this is a randomized strategy. You're picking A with the row player is picking A with probability x1 and B with probability x2. So you can think of this as if you were playing this game many times in a row, then you wouldn't want to pick the same action each time. You're going to want to have some aspect of randomness in your strategy. So this would be how you decide what you want your probabilities of choosing each action to be. So what's the optimal strategy for row? Well, we're going to want to choose a strategy such that even if you were to reveal your strategy to the column player can choose one of the two actions, but then you want to maximize your score. So in other words, you want to find x1 and x2 that maximizes. So we can calculate an expected value of this grid. So we were going to want to find the x1 and x2 that maximizes the minimum of the two expected values. So if column were to choose C, then the expected value of the game would be -4x1 plus 2x2. And then if the column player were to pick D, then the expected value would be 5x1 minus 3x2. So we're going to assume that the column player is good. That after we pick a strategy, x1 and x2, then the column player is just going to pick whichever one gives him the best expected value, the minimum expected value. So this can be written as we're trying to find the x that maximizes the minimum y such that we're trying to, this is how we write the value of the game, g, I, j, x, I, y, j. So g here is the game matrix, the payoff matrix. In this case, it's this grid here, -4, 5, 2, and 3. So the value of the game, so I guess I should clarify, you can calculate the probability of each square in this grid appearing by multiplying the corresponding probability. So if you want to see the probability of this -4 occurring, you would multiply x1 times y1. And then we can calculate an expected value for the game as the sum of I, j, g of ij times xi, yj. This is just summing over the expected values of each square, which is, we can also write this in matrix vector notation as x transpose g, y. So x and y are vectors and g is a matrix. So again, like the row player is trying to maximize this value while the column player is trying to minimize this value. So now we want to try to find the x1 and x2 that maximizes this minimum. So you want to try to maximize this value no matter what the column player chooses. Now you can represent this with a linear program. The way you would do this is you would define an additional variable, let's call it z, and say that z has to be constrained by both of these values. So let's say we are trying to maximize z such that z is less than or equal to -4x1 plus 2x2, and z is less than or equal to 5x1 minus 3x2. So these two constraints enforce that z needs to be less than or equal to both of these values. And because we're trying to maximize z, this is equivalent to just taking the minimum of those two values. Of course, we also need constraints on x1 and x2. So since x1 and x2 are probabilities, they need to add up to 1. And x1 and x2 both need to be greater than or equal to 0. So now we have here a linear program. If we solve this linear program, we can figure out what the maximum value of the game is, the expected value of the game, when the row player reveals their strategy first. So there's 3 variables here. So we know that because the optimum in a linear program needs to occur at a vertex, and each vertex here, because there's 3 variables, each vertex would need to be the intersection of at least 3 constraints. So I'm going to take the first 3 constraints here. So the z constraints So these two constraints are going to be equal. So z equals -4x1 plus 2x2. And the second constraint is also met with equality. And then, of course, we have the x1 plus x2 equals 1 constraint. So now we can solve for x1 and x2. First, let's set these two equal to each other. Plus 2x2 equals 5x1 minus 3x2. So we can do this with some algebra. 5x2. So x2 equals 9/5 x1. And then when we plug this into this equation here, the x1 plus x2 equals 1 constraint, then we get x1 plus 9/5 x1 equals 1, or x1 equals 5/14. And similarly, x2 would thus equal 9/14. So then this is the row player's optimal strategy. Row should choose A with probability 5/14 and B with probability 9/14. So let's calculate what the value of this would be. So again, we're going to plug this into this first expression here. So we're going to assume that the column player is always going to choose C, and then we'll see what the expected value is. So -4 times 5/14 plus 2 times 9/14. This is going to equal -1/7. And if the column player were to choose D instead, 5 times 5/14 minus 3 times 9/14, that is also going to equal -1/7. So now we've seen that this vertex is the one that satisfies these three constraints with equality, and it also happens to be each of the x1s and x2s do follow the fourth constraint that both of them are non-negative, so that's good. We still need to check if this is actually a maximum. So the other vertices of the feasible region are all going to involve this constraint that x1 and x2, either x1 or x2 are 0. Well, if x1 is 1 and x2 is 0, then the column player would just choose -4, so that wouldn't be good. And if x1 is 0 and x2 is 1, then the column player would just choose -3. And both of those are less than what we would get with this mixed strategy, so that's good. Even though this value is negative, meaning this game is slightly in favor of the column player, this is the maximum that the row player can do. It's the way that the row player can take the least loss. So we've figured out what the optimal strategy for the row player is, and we figured out the value. Now let's try to do the same for the column player. So again, the column player will be now trying to find y1 and y2 that minimizes. So the column player now is trying to minimize this value. So what are they trying to minimize? Well, you're going to assume that the row player is going to maximize. So if column player were to pick a strategy y1 and y2, then if row plays A, then the expected value would be -4y1 plus 5y2. And then if the row player picks B, then the expected value would be 2y1 minus 3y2. So -4y1 plus 5y2. And 2y1 minus 3y2. Those are, again, the expected values. Okay. So now, again, we can write a linear program for this. So instead of maximizing now, we're going to minimize another variable, let's call it w, where w needs to be greater than or equal to both of these values. So negative 4y1 plus 5y2, and w is greater than or equal to 2y1 minus 3y2. And again, y1 and y2 are probabilities, so they need to equal 1, and they need to be greater than or equal to 0. So this is our linear program, and we can solve for the optimum of this linear program the same way. So I'm just going to kind of do this quickly here since you already saw it. So y1 plus y2, I'm setting the first two expressions to be equal to each other. y1 minus 3y2. So this becomes 6y1 equals 8y2. y2 equals 3/4 y1. Therefore, y1 plus 3/4, y1 equals 1, and y1 equals, so this is going to be 7/4, so this is going to be 4/7, and y2 is equal to 3/7. So this does happen to be the optimal strategy for the column player. So now the expected value here would be negative 4 times 4/7 plus 5 times 3/7. That is going to equal negative 1/7, and 2/4 minus 3/7. That also equals negative 1/7. So this holds. So now, as you can see, we got the same expected value, negative 1/7, no matter whether the row player went or the column player went. And in fact, this is to be expected because this linear program here is actually the dual of this linear program here. You can check that they satisfy duality, which means that the optimal solution in this linear program is equal to the optimal solution in this linear program. So thus the answers you get are going to be the same. So therefore, we can say that no matter which player were to go first, if whichever player, even if they were to announce their mixed strategy ahead of time, the expected value of the game is still going to be the same either way. So this can be stated, this is called the min-max theorem, which says that if the row player goes first, so if you were trying to find, if the row player is trying to find x that maximizes what the column player is going to choose y in response to of the value of the game, ij, g, ij times x, I, y, j. This is equal to if the column player were to go first. If the column player were to find the y that minimizes a maximum that the row player will play in response. J of g of I, j, x, I, y, j. So this is the min-max theorem, which states that even if one player were to announce their mixed strategy ahead of time, and they were to play that mixed strategy, then still neither player is going to have an advantage in terms of expected value.
What's up, guys? So today we're going to be talking about flow and Ford Fulkerson, and right now I'm going to be walking you through sort of finding the max flow of this graph right here. So the two things you need to keep in mind when we start talking about Ford Fulkerson and max flow is that the amount of flow going into a node or vertice has to be equal to the amount of flow going out of this vertice. That's called the conservation of flow. The other thing we need to keep in mind is that we cannot sort of push more flow through this edge than is the capacity of that edge. So right here, you can see that the capacity of this edge, that's going to be 3. We cannot start pushing 4. We can think about this edge as like a pipe. Pardon the poor illustration, but I think it does the job. So we can think of this as a pipe with water coming out of it. And if we push more water than the pipe can handle, or the pipe is rated to, then obviously we're gonna blow up the pipe. Or if you want to think about it another way, if we push more current through a wire than is in the wire, than the wire can handle, then we'll blow up the wire. So bad things can happen. So what I'm trying to say is we can't push more flow than is the capacity of this edge. So on my left here, we've got the graph that we're about to do max flow on. This is going to be what's called a residual graph, and I'll explain what that means in a second. But this graph on our right is going to be our current flow, and that's going to keep track of essentially all of the paths we built up so far and the flow we've built up so far. So without further ado, let's start getting to it, and I'll start showing you, sort of visualizing how Ford Fulkerson works. So Ford Fulkerson works off of a set of augmented paths, such that an augmented path is a path that goes from S to T and is some arbitrary path in our graph. It doesn't really matter how we get from S to T. And if we take the set of all of these augmented paths until we're saturated, and then take the bottleneck values of all of those, then that will give us our max flow. So let's start putting those words to action right now. So Ford Fulkerson is deliberately vague about how you traverse this graph, and so for this example, we're going to be doing DFS. And DFS means that this is essentially a random traversal of this graph, because we can pick any neighbors, right, at any edge, so it'll essentially be random. So we're going to pick a random augmented path right now. Right here, and right here. So for this path, we can see that that our bottleneck value will be what? So I'm gonna ask you guys that question. So what's our bottleneck gonna be? Go ahead and pause the video and just briefly tell me. And I'm gonna start the video back in 3, 2, 1. So the bottleneck value for this path is gonna be 1, correct? Because if we remember our second property, if we start pushing like 3, and just because this pipe can handle 3, if you start pushing 3 in this pipe will blow up right here. So that's no good. So our bottleneck value is going to be 1 right here. So let's start pushing that path. Let's start pushing 1 through. So we go here, and that's going to be, so we're pushing 1 flow. So that means this edge is at capacity. So we've got 0 flow left. For this path, we've got one unit of flow left to exploit. And here we've got 2 units of flow to exploit. But how do we know that this augmented path is the optimal path? And it's actually not the optimal path, but we'll get to that in a second. We actually don't know. So what we're going to do here is we're going to give us a mechanism to sort of backtrace and undo our mistakes and traversals through this graph. And what that is what that's going to be is the residual graph. So the residual graph, I'll mark in a different color here. And it's going to be directly undoing the augmented path and operation we just did. So for this, it's going to be one flow in the reverse direction. This, it's going to be one flow in the reverse direction, 1 unit of flow in the reverse direction, and this is going to be 1 unit of flow in the reverse direction. So there we have it. That's one augmented flow graph. That's one augmented path done. Let's update our path right now too. Let's do this quickly. It's gonna be 1, 1, 1. All right, now let's pick a different path. I want to keep that 0 there. Okay, so we're gonna randomly pick a different path. Let's pick, this is all random, by the way, DFS. So let's pick this one right here. So what's going to be our bottleneck now for this augmented path? Go ahead and pause the video, and I'll say it in 3, 2, 1. It's going to be 4. So if you answered 4, congrats. I'm proud of you. Anyway, for 4, we're going to, so 4 is going to be this node right here. We're going to essentially say, all right, this has reached capacity. We can't push any more units through that one. We can still push 1 more unit through this one. So if there's any other path, and we can still push 1 more unit through this one. Obviously, we must put our mechanisms for replacement. So let's go back here. Put a residual graph, right? So we just pushed 4. We can undo it by pushing 4 back. Undo this. Pushing another 4 back. We can undo this by pushing 4 back. Awesome. So then let's quickly update our current flow graph right now. So this is going to be the path that our flow is going through so far. So if you're building out this pipe for a maximum flow problem or network, this is the sort of stage we'd be at so far. These would all be 4. All right. Now let's pick another augmented path. So we can't pick this one, right? We can't pick this one. So the only thing left is here. We have 3 here. So we go here, pick 3, pick 2. We can go here and pick 1. So as you can see, the bottleneck for this one is going to be 1, 2. And then let's update our current flow. So we've pushed 1 unit of flow, right? So we pushed 1 unit here, pushed 1 unit here, pushed 1 unit here, and then we've actually now pushed 4 plus 1, right? So we pushed 5 units there. So 5. Awesome. All right, now let's see if we have any augmented graphs left. Like, let's see if there are any more paths from S to T left. First, let's remove this for the sake. Oh, almost forgot. We need to put our residual graph. So this is the back edge. This is the 1 unit back edge, and this is a 1 unit back edge as a residual graph. Anyway, let's go through here and let's see if there are any other augmented paths left for us to take. Yeah, I can see one. So we can go here, here, and here, right? So let's do that. So what's going to be our bottleneck? It's going to be 1 again. So now this is saturated to 0. This is saturated to 0. This is saturated. This still has 1 unit of flow we can push left. Because of the bottleneck, we can't push more. So we still got 1 left. And then let's update our residual graph, right? So boop, boop, boop. Those are all 1s. Now those are all going to be 2s because we're adding 1 unit of flow back edge. 2, 2, 2. Okay. And then let's update, obviously, our graph as well. So this is going to be 2 now. This is going to be 2. And this is going to be 2. So I think that's going to be it. I think that's all. Every outgoing from S is now saturated. Like, so now you can tell that there are no more augmented graphs because regardless of how we get there, there's no path from any one of these edges such that we can get from S to T. Like all of, if we were to draw another augmented path here, then the bottleneck value would be 0, which means we'd be able to push no flow. So yeah, you can see here, I think this would be the cut we could draw. So you can see here, any path that takes any of these edges, you can see that this is 0 right here, this is 0, this is 0. There is no way for us to get from S to T now because we've exhausted all paths, including back edges, which we could have used these back edges at any time as well, but we just chose not to because that's just how it turned out so far. But if you're doing this on another graph, you could have just as easily used a back edge, just like we would have used a front edge, just like we would have used any other edge. Anyway, so this is now our graph right here. And our max flow is just going to be simply the sum of all of these edges. So it's going to be 2 plus 2 plus 2 plus 1 plus 1 plus 1 plus 4 plus 4 plus 5. So it's going to be 8, 9, 14, 16, 18, 20, 21, 22. Max flow is going to be 22. Yeah, so that's how you do a Ford-Fulkerson algorithm. I hope you enjoyed it. Thanks. My name's Abhi again, and goodbye. Have fun.